You are mute now. Can you hear me? Can you hear me all right? Hello.
Hi, yeah, we are back.
Can you hear me?
Yes, yeah.
So there are
But for
two
some
self.
reason you appeared twice.
I know. I have
Still
to.
spot. Huh?
I have to get
Okay,
rid of
there
one.
we go. Now it's just. Oh, okay. You were the host, and probably you were also acquired. Okay.
Have too many of me there. Okay, so why don't you show? I like the flux. You took the measurements of flux of helium line over two consecutive periods, or the one that was available. Somebody is coming in. Let's see who that is. Shaunak.
Hey,
Oh,
Sean.
Shaunak's
Hi.
there. Hey, Shaunak.
Hi there.
Hello. So I saw during the week you send your flux measurements over those consecutive nights. I would like to talk about that thing or
Okay.
discuss that part. And Shaunak, were you able to run the programs?
Not quite. I'm still working on getting that into IDL.
Okay.
That's why I'm using my Windows today. So I think we could probably run
Okay.
through that process quickly.
Okay, so maybe I should start sharing my computer, and you could start sharing yours so we can see what the problem might be.
Okay.
Okay, wait a second. You're not seeing my screen, are you?
Not yet.
Okay, so then you can start sharing your screen. Yeah. So if you go to the bottom of the
Okay.
screen, you have a green command,
Yeah.
and then you can share the screen.
Okay. Do you see my screen?
It's all black.
Oh.
Can you guys see it?
No, it's all black.
Yeah.
Okay. Let's see.
Okay, that's getting better.
Do you see anything right now?
Yeah.
Yeah, we can see.
Okay.
Are you sharing just one? Okay, good.
Do you see the IDL?
Yes.
Good.
Yeah.
Okay.
But you don't have the workbench, do you? I don't think this virtual machine is the one we want.
Oh, is it not? I think I may have opened the wrong one. Maybe they should have they should have the folder in it.
In fact, I don't know what this virtual machine is. You wanted the workbench.
Here we go. This is the workbench.
Yeah. There you go. Yeah,
Okay.
that's better.
And so this thing over here, I presume, is where we put all the files, right?
Yeah, your routine is correct.
Okay. So
and you have your command line towards the bottom part.
Mm-hmm. And let me take the files that we have. Okay. So, and so I just need to put these files into my directory, or am I able to drag them
It's
inside?
always recommend that you have a directory that is one you are developing your disposable routines or those that you are developing. I think with this workbench you can create a project, which is a folder called project, and you can give a name you want, and then you can in it address all the routines you're using in a given project. I don't know much how to do. I didn't have time to invest in learning more about it. Probably I should. But what I did, I went to in your case, a Microsoft folder, and then I create a folder named Pro, Pro for all the routines that I'm developing. And then anything that I develop, I load it in there.
Okay, so I think it would probably go in the
I wouldn't put it there because those folders are folders with routines that you constantly use to run anything. It would be something more specific to what we are doing now, which is to understand TW Hydra. I would maybe put it in, I don't know, if you have in your documents, if you have a folder name, let's say PMS for premium sequence or TTS, and then from there you create a subfolder or a subdirectory with TW Hydra, and then from there another one for Pro, for routines. And then you load all these routines in there.
Should it look like this?
These are files. They looks like, I don't know what they are, but they look like low resolution data.
Yeah, this is low resolution.
Yeah. I would create a folder named TW Hydra or Pharos, and then from Pharos you would create a folder or a subdirectory named TW Hydra.
And then can I put the routines in here?
And then I would create now a subdirectory named Pro for routines.
Okay.
And then on that subdirectory, I would load all the routines. Yeah.
Okay.
By the way, while you do that, Lee Rottler put down 177 new files of TW Hydra. Out of these 177, the first two were bogus, and I don't know what they are. One means something weird, and the other one it looks like a normal main sequence star. So he downloaded them all, and I have the fits file. So when you guys are ready to work on it, I have it. And then I've been working on free time, the time that I have, on try to tweak those routines that we use up to now to work on these files and make everything automatic. So now we have 175 files to analyze, and not 92.
So that's on top of the 92 we already have?
That's a good question. I don't know if there is an overlap. I assume there is an overlap. So this 92 should be included in 177, but I didn't go to details to figure out which one is what.
Are those guys the same format, in SAV format?
Well, it's in FITS format. So ISO is going to give them in FITS format. And what I did, so Lee Rottler download them in Dropbox, and I read them, and then I load them in one of my subdirectory, and then I convert them to SAV file.
Cool. My point is with what we have here, if we can right now open them. If it is the same format, we can open them right away.
Yeah, I mean, once we do the steps for one thing, I mean, for the others, it's just automatic. Just to make small tweaks and we are there. And Philip is starting class next week, right?
I actually already started this week, yeah.
Oh, you already did? Oh, God. And Shawnike is not next week, it's the week after, right?
No, next week.
Oh, next week.
Yeah.
That's it. So see you next year. Let's finish the project. Can't do more. Make sure you get the last email I sent, the last routines, because they all had some small tweaks.
Okay, so okay, yeah. So I have these three routines.
Okay, so
I
the
think
first
I'm still-
one, let me see what they are. Where are they?
I think I'm still missing the veiling routines.
Yeah, so let me send the veiling then.
Okay, I have the veiling.pro one.
Oh, you found it?
Yeah.
Make sure, see if the one that has a bunch of ifs and conditional for wavelength range in the very beginning, if you can open them.
Yeah, I can't open it from here. I'll probably have to open it once I download it into IDL.
To the glider.
Oh, it actually just I can just drag this into IDL and it opens.
Can you?
Yeah.
I can't find the routines.
I think in the file you might need to change the path names, since I think they're configured for Celso's machine.
Right.
So wherever you download TW.
Right, okay.
Let me see if the Soundbox paper is one.
Okay, so besides these four, was I missing anything else?
No, I guess that's it. You just need to make sure you have the addresses all set, and you compile them, and would be nice. I mean, why don't you have them there? So it's good you have them there. If you, I don't know if you have the time to do anything before class start, but if you do, and if you find any pitfalls, I would ask you to email me, and then I can work with you. And make sure at least you have everything ready to go.
Right. And then I should probably make separate subdirectories for the files that we have, or like the FITS files.
For the yes. Those for those files you have to go to Dropbox and download them. I didn't put in the Dropbox the new files that I'm working now because I want to, at least these old files, I wanted you to get some data and some analysis similar to the one Philippe's done, and then we can discuss results. So once we have these results, we can have some idea how this profile behave, and then we can go to those new files that we just download. I'm working on them, but I don't think I have time to do any analysis or collect any data or do any measurements. So if that could be done in the next, tomorrow, Friday, that would be great, because then on Sunday, if we could find a time, at least 1 hour, just to get our kind of what's going on together before class starts, that would be great. Because I would like to set some guidelines, some landscapes for us to meet. Otherwise, we're gonna lose all this momentum we had so far. It's gonna go away. When we get together again 3-4 months from now, when class stops or something, probably there will be another 300 files there for us to work, and we should conclude something before class starts. So I would like by Sunday, if we could come up with some results and say, okay, that's what we got, that's what we can find in the literature up to now, and that's how we should progress if we have the time to work on it. But we should have something concrete done, otherwise certainly we will lose, and that's going to be frustrating.
Right.
Okay. So I start rereading the paper we wrote on TW Hydra using Ferro's high resolution. In fact, the paper was primarily written by Sylvia. Sylvia, she was a postdoc in Berkeley. She spent there 2 years, and part of the training she did was to learn these IDL routines that does the decomposition of line profiles. So, and then when she went back to Brazil, I asked her, listen, I have 42 files. Would like to come and work with me? And then she came. By that time, I had initiated the analysis in low resolution data of TW Hydra. And the difference between one another is FIRS doesn't give you flex calibrated data. So we don't know how many ergs per square centimeter that energy is. You don't have that because everything is normalized. When you do spectrophotometry, you have a spectrum distribution, but also you have that calibrated in flux. And we attempted to do that. Some of our nights were photometric, not all of it, but some of them were. And then we try to use that to model the spot variation, how much energy was coming out of these accretion funnels. So that was one paper, and then she joined us, and then she did the analysis in high resolution. So what I would like to do today is to go over some of what she found in the helium line. That's where I would like to start, because it seems to be one that we can derive lots of good information and learn a lot about it. Okay. So, but before going there, I would like if Philip could show what he found, and then we can move up to the article, to the paper.
Sure. Yeah. Should we get them back?
So then I think Shaunak should release.
It's I believe so.
Shaunak should release, and then Philip should take it over. Hey, Vikas. Vikas is there.
Hey, Celso, how are you doing?
I'm doing all right.
Doing good. So what I'm doing right now is I'm reading through the Weiss paper, and I was going to basically type up some notes and kind of share it on a Google Drive or Doc for you guys, just to kind of get my summary of what I think is. So that's what I'm doing right now. Is I'm doing some paper reading on my end.
So are you putting your notes in a Google Drive? Do we have access to?
Yeah, I'm going to put it into a Google Drive, and then I'll give you guys access to kind of just a quick notes and summary of what the paper is about, and kind of keep keep I guess you guys maybe use Dropbox. Keep a central location of just notes in general on the paper. That's
good. That's a good idea. And
You
tomorrow we have a public viewing, and don't forget that.
We have a quank here, right? Some quant. Okay. Okay.
Philip, we have two of you.
Yeah. On. I think there's an echo.
There is an echo. Yeah, because two of you are there. There was two of me, and I killed one of it.
There we go.
Okay.
So now I'm on my Mac, and I can share the program we use to get those results.
Okay. So you are going to show the flux, the calibrated flux of helium line.
Right. What we sent in the email.
Okay.
So. Just a moment.
This is another one. Okay, I think another should be open.
Man, that's a big file.
Yeah.
Just run it once again.
Yeah, there we go.
Oh yeah, and I think that there is one trick here for showing everything. Okay, that's it. You know, we have to. But I think okay, we have to run it once again. Run all. Why it is only this? Okay, because we chose. Okay, that's fine. You can share it. Did you share the screen or not? Oh, okay. Yeah. Celso is uploading, right?
Sean X is copying some. Yeah.
So who is this Sean X screen?
Yeah.
Oh, I thought Philip was going to show something.
Oh, yeah, here, I'll stop sharing.
Yeah, there you go.
Okay.
Oh, I thought Philip was pulling up a file from somewhere. I say, geez, this is a big file.
Right. So can you guys see right now my screen?
So yeah, I can see a program, Jupyter, Evccsi CSF flux time. Okay.
Right. Okay, so here we have record numbers. So what we did was on my Windows machine where the IDL routines are running, we got the flux from the Helium 1.pro program, and we got about 30 or so records done from 1 to 30.
1 to 30, okay.
Yeah, and it appears that in terms of consecutive days, 6 to 24 were taken pretty closely together, and we have this kind of.
So wait a second. Stop there. Stop in one of the. Okay, stop there. What is this?
So this is flux versus Julian date.
Okay, let me expand here. 5, 4, 2, 1, 6, 2, 2, 8. So it's about 12 days. Is that what it is? 12 consecutive days.
And I think there are 2 observations per day.
Oh, 2 observations per day. Okay. Is this flux corrected, or is this the flux already corrected by Veiling for Veiling?
This is how we got the flux from the save file. How the flux were produced from this routine. What was the name of routine?
HE5875.
So according to there is no systematic variation. I don't think. It should be all over the place.
Would you mind putting everything together? Because I think that there is something like, go up and put for range from 1 to 30. Include everything, 1 to 30. This is all observation, 1 to 30.
So this is 1 to 30.
Run everything again.
Yeah. Okay. Well, is this Python?
Yeah, this is Python.
Cool.
This is Python.
Looks clean. Okay.
Yeah. Okay. Let's see down there okay. These are the observations so far. For 30 days. So okay. I'm wondering. So when I was looking at the data, is it, for example, here about 54,200? Is it
54,200? Okay, that's towards the end. Okay.
Yeah. I was just wondering, can we expect here some kind? Do we need, let's say, one month observation? I'm not sure, but actually, from what we sent, it is very difficult to think about for the flux for the periodicity.
The previous graphics that you show, I didn't see any kind of an obvious trend. I couldn't see it.
Yeah. Phil, could you please show that way? Show the veiling. That is the flux, and here is the veiling.
Yeah, it's hard to tell. It seems to be just yeah, we can't see anything.
Yeah. Put again from 6 to 24. 6 to 24.
So 1 to 30 means, yeah, because the span in Julian dates there is 200 days. It's almost a year.
Yes, that's right.
Yeah.
Now, right, okay, let's see what we're getting for.
Okay, that's better. Now we have 16 to 28. We have 12 days.
But if you go down there on the veiling, there is something, I mean, I'm not quite sure. Can it be some kind of beginning of periodicity with 20 and something days? That could be the first wave of a period.
So we have so the veiling diminish, and then if we could believe it started to go up again, but we don't have more consecutive data.
Yes,
so,
the more consecutive data, it goes to another cluster. Here it stops, and there is a few more days, and then starts another cluster.
16 to 24 is what? 8 days. So we have 8 days of falling, and then it starts to grow again in the next 4 days. Well, it would be nice to have more, but I have that data, don't I?
We got only the first 30 days, so we are gonna get further. We have another 60 days to go.
Oh, I see.
Yeah.
Well, so based on this, we can't say much. What we can say is the veiling is steadily decreasing from Julian date 54216 to 54224. So there is 8 days in which the veiling decrease, and then we can't say much besides it seems that it goes up.
So this evening, at least till the end of the week, we are gonna make the next 60 observations.
Yeah.
Because it is just we figured out how not to screw the files.
That would be good because as far as I remember, there are 2 chunks of data. There are consecutives.
Yeah.
And then we could.
This is the first chunk. This is the first chunk.
Do you have flux on it? The helium flux on those days? Measure? No.
Yeah. This is the flux is here.
Oh, you do?
Yeah.
Oh, okay. Well, where is it?
Here. Yeah. We did different graphics, but we can put it on one graphic.
So this is the veiling, the flux already corrected. Yes. Yeah, the flux doesn't change. It seems to be the same.
The flux is, yeah.
There's this isolated point, the first one, that's some sort of an outlier, but everything else, I don't know, we can't say much.
I think it works for me very Gaussian distributed. Very stochastic.
Oh my God. You are saying too much, my friend.
How long is the stellar rotation period?
4 days, I believe, or 5.
It's 4.5 days, according to some, and I think we put that in the paper. There was other people mentioning 2.9 days. Yeah.
So maybe what we're seeing in the veiling data is that as the star is rotating, you're seeing different profiles of the inflow, and so maybe that contributes to less or more veiling depending on where you are in the stellar rotation period.
Well, when the star rotates, because the veiling. If the veiling comes from some region that is attached to the star, which we think it is, so then measuring veiling or tracing veiling, we could trace the stellar rotation, right? If the accretion rate is steady. Does that make sense? Now, if the accretion rate is a big thing, right? So big that the variation in accretion rate over a period of a few days is more important than the flux emission that comes from the hotspot, considering the fact that the star is not edge on like this, is face on. So we might be seeing the spot as the star rotates. Does that make sense?
Right.
Because the star is rotating, the spot is just going around in circle. Let's say if it's a perfect 9 degrees, so we are seeing the pole on right there.
Mm-hmm.
So the spot is just rotating. We don't see any variation as the star rotates.
Right.
So any change in veiling would be due to the accretion rate. So it's more chunk of materials going to the star, and then we see this reflected in the emission, the excess emission we call veiling.
So if the other observation is if there was a periodicity, because the period is between, we know it is between 2 and 5 days, probably it is 4.5.
Right.
12 days, if there was something periodic events, 12 days would be kind of sufficient to see further signs of periodicity.
Yeah.
And on top of that, we have 2 observations per day. So that means it is pretty conclusive. If there was a periodicity of the flux or the veiling for this observation, it would be pretty conclusive.
Yes. I mean, based on this data here, which is sequential, we can't say much. For instance, this point, you have this point here, right? Can you see my cursor? No, you can't see it, right?
No.
Okay, so the extreme point in the left-hand side. Let's say take that point and then go down, keep falling. So that's good, and then you start going up. Go more to 54220. 54220. So you got the lowest part there, and then you start to go up in 54222. But then you have these points right there in the bottom part. So
I see what are you trying to say. So
this point is saying, listen, if these points are real, then we don't have a trend of falling down and then going up.
Yeah.
So if you want to be kind of curious and make sure everything is right, I would revisit these 2 points and see if they make sense. But I mean, why not revisit everybody else, right?
Yeah.
So in other words, based on the data that is there, we can't say much.
Hmm?
So go ahead.
You mentioned that there are 2 clusters of consecutive night data. So we are going to do that, and we are going to take a look how it looks like.
Can we get together on this point on Sunday?
Yeah, of course. Yeah.
Okay.
We can meet on Sunday, and we can go.
Yeah, so let's meet on Sunday, and let's have veiling as one of the main issue, and then the helium one also as the main issue. And as far as I remember, the routine that is calculating the flux now, calculates not corrected flux and corrected flux. So we have the 2 measurements in there.
So this is what we were taking. So these are the 3 measurements. What this routine, just a second, it was returning, just a second, what was the name of this guy? This is the line, what we were getting back from line flux. From line flux, this is the flux, this is the and these are the 2 parameters, and the veiling was separate, what we were getting.
Okay, so the one in the middle is the wavelength. The one in this extreme left is called equivalent width, and the one in the right is called line flux.
So we were taking the white. This is we are taking the 3rd parameter. This is the white.
I would take the 3rd parameter, line flux. The equivalent width is.
This is the one. This guy is the red guy.
That's the one you should take. Yeah, the line flux. Yeah.
And below, so because you are saving the here in the file the veiling, we were taking the. But here from these 3 parameters, what we are getting back from the wavelength, I'm looking at the program. The flux, wavelength, and flux and everything we were taking.
Right. Well, can you go back to veiling now?
Yes, of course.
You could maybe say that there is a correlation between the veiling measured and the flux. See, the one in 54216, the highest veiling you measure, is also the one with the highest flux.
That is correct.
Yeah, so that's something that we can say. But
the veiling and they are pretty proportional both. Let's try to put them on one graph here just before this show. So let's put that here. Now they will appear together.
Oh, okay.
Yeah, just let me put this in commentary. The next line, Tati. Also the figure in commentary. Yes, put it. And this 4 also goes in commentary. And everything will appear together. Now.
Oh, this is very nice. Yeah. Oh, that's very nice.
Yeah, this is what we are getting, but because the veiling is normalized, we are getting it a little bit lower.
Well, it seems that accretion is controlling the fluctuation. That's what's being shown there. I mean, in some extent, the flux goes down and starts going up again.
Yes.
It would be nice to see these two, the two measurements are at around 4, 5, 2, 2, 3 in red.
4, 5,
2, 2, 3 in red.
These guys.
Yeah, those two and the one on top. So if you take the average of those two, it's going to be right in the middle. And then you have a trend that reflects the trend you see in veiling, you know. So I wonder if there was something. I would revisit the flux measurements in those 4 points around 5, 4, 2, 2, 3.
I have a quick question around. Okay, so I'm looking at this graph right here. So the red is the actual spectral dots from the
flux.
Well, from the flux.
Yes.
And the blue.
So think about energy that comes out of this line emission.
Okay. So the red is the emission line, and the blue is basically what you mentioned in the last one.
The blue is a continuum that is formed somewhere close to the star. That's how we interpret veiling. So if you think of a gas that's falling towards the star, so you have different regions in which the gas temperature increase because the density increase, the kinetic energy of this falling gas is also increasing because it's getting faster as it gets close to the star. And eventually this gas is decelerated because it's now colliding with the stellar photosphere. And then they call this a pre-shock region. Shock region when this gas is stopped, and you have a post-shock region where this energy is basically released. So some people interpret the veiling as being some emission that comes from the post-shock region close to the stellar atmosphere, which means it should be anchored in the star itself. So when the star rotates, if you have some hot region there, you should be able to see this hot region modulating the stellar flux.
So what we are concluding here is that since the flux kind of reflects the energy of the accretion, that means the excess, that means the veiling, the excess of energy is correlated.
So the veiling is some people, and I think we did that too, they associated the veiling as the amount of gas falling, as the accretion rate, and then you can do some simple calculation to determine how many solar mass per year is falling towards the star as a result of that.
I see.
Okay. So how much
now,
is actually
the line flux is different. The flux, the one in red, is a different ball game because this line flux, depending on which line you're looking at, could be formed in the funnel that is falling towards the star in different regions. And some people like Frank Shu, they also suggest that the stellar magnetic field lines twists and comes out of the star, or in fact out of the circumstellar disk, and then and pumps the stellar wind. So you might find in an emission line indicators of gas falling and indicators of gas coming out of it. So the two of them kind of are working together. So it's a complicated issue. So that's why people like us and Sylvia and others, they try to take several observations, consecutive nights, so that they can probe if some variation in features that are associated with gas going towards you, observer, which means blue shift, has some correspondence with the stellar rotation, or some other features that are more associated with the gas falling towards the star, which means red shifted type of features, are associated with accretion rates.
Oh, so we just measure the blue shift, red shift also to measure the level of accretion as well and how fast.
You can, with the line it's complicated because the line emission is not necessarily coming from a, as we say, optically thick gas. The gas that is one photon is associated with one transition in the gas, so that you can take that emission and associate it with the gas temperature. So sometimes the gas is transparent, and then you have emission coming up from different locations, from different positions in the gas. And then since in different locations the gas is moving at different speeds, at different velocity, you see different features in the line emission. So it's a complicated issue. As far as I remember, me, Sylvia primarily, and I, we didn't go in a lot of detail. We tried to discuss blue shifted emission as being the one related to expanding gas or outflow, and red shifted emission or components as being due to gas accretion, without trying to model line emission, which is complicated.
Okay, interesting. I see.
Now, in an advanced stage, if we can, I mean, after a while, once you start seeing these profiles so many times and repeating and getting used to the trend, one thing we might be tempted to do is to do some imaging of a star with spots and with prominences or loops, and make that thing rotate using some sort of a software, and see if the image we are imagining is the case, can reproduce the variability we see in line emission without doing any major modeling, right? It's just a visual appeal for people who might visit.
That will be interesting. Simulation to animation.
Yeah. I'm just thinking ahead in the future.
Would it also be useful to know the variation in accretion rate?
Yes, and that we can have an idea of it with veiling itself. So we assume the emission is kind of isotropic, and then we can take the veiling measurement based on the type of star we have, so we can convert that into flux or a certain amount of energy, and then we can associate it with an equation, and then it gives accretion rate, which is in the papers is M with a dot on the top, so dm/dt. For the star, I think it's 10 to minus 9 solar masses per year. 10 to minus 9.
Sorry, this is the accretion rate, right?
Yeah. Right.
Oh, and then by looking at measurements from different Julian dates, we can compare how the accretion rates tend to vary.
Yeah, that's what they did here with the blue. See, there's blue dots in the graphic that's being shown. So if you think these blue dots somehow can be translated in accretion rate, so you have a steady decline in accretion rate over 6 days,
yes,
and then you start kind of kicking up again. So people this is science we did in 2010, let's say. But since people start finding planets around stars, the exoplanets, now I suspect that all this data that is being collected in the literature on TW Hydra that we are using now, I think the main point of these papers is to discuss possible planet formation close to the star. Because if you have planet forming next to the star in the circumstellar disk, so you have some chunks of gas kind of concentrated in different locations, right? And then necessarily the accretion rate is not going to be something steady. It's going to be very over time.
What are you saying? Because of the planet circling, they are big, and they're causing turbulences in the.
You might have gaps. You might have all kind of rings. You might have.
And
all
we
kind
get
of
even more stochastic in the measurements.
Yes.
So would planetary formation cause the accretion rate to slow down?
I mean, the accretion the accretion towards the star is not. So if this is a star, so the accretion is not something radial like that, because you have the gas falling Keplerian, and then it takes some time to spiral, and then you have viscosity in the disk. This viscosity implies energy being lost, so the gas lose angular momentum and then spiral towards the star. So and eventually hits the star either with this magnetosphere bringing the gas disk to high latitude, or as we thought in the 80s, the disk would go all the way to the equatorial part of the star. So it doesn't seem to be the case. But if you have a planet formed in this circumstellar disk, you're going to have all kind of gaps and inhomogeneities in the disk itself, which will trigger some different accretion once the star is in the process of free falling on the star, right?
Mm-hmm.
I mean, so basically the gas will Keplerian rotate around the star, and then eventually it's going to free fall there once it's decoupled from the disk itself.
So that means we can, assuming that we have, so to say, very accurate measurements, we can speculate that stochastic in the measurement.
Absolutely, my friend. That's the good thing. Okay, we have this data, right? And we think we did a good job. We check and recheck, and we have several people recheck. So that is what it is. So what sort of a story can we tell about this? That's the fun of science.
Yeah.
Right? And no one else can. I mean, you guys can because you have the data. That's the whole point. Right? And then you can say, well, you know, the accretion rate has a short-term variability of blah blah blah. So it's a number you can measure. You know.
Till Sunday we will finish everything. We will be finished because we messed up the data. Something we had a very small bug.
Okay.
Actually, from the program, what we got by mistake, we deleted something from a line, and that messed up our data, and we had to recreate it again. But we know how to do.
So the only thing that I would ask you to do carefully is when you measure the flux, make sure you always measure on the same points.
Of course.
Yeah. Remember the hidden line when you choose the point should be close to 1. Because it should be well normalized, and so that therefore we are measuring always consistently in the same baseline. Yeah. And I would try to do the same if I can. I would try to finish all this 9.2. If I can, I will start working on the other 177, which incorporate this 9.2. This is one thing. The other thing, I would try to do some testing with routines that do periodic periodogram analysis of data sets. So basically what they do, they take the data and they fold in different periods and then see which one is the most probable one.
I see.
Yeah, I found some IDL routines that do the job, the trick, and I see if they are reliable.
But for that, we need to choose something like periods. Then we can overlap the different teeth.
Yeah. For instance, if you fold this data here, the blue, I mean, you don't get anything, right? Because you can see visually. You don't need software, so you can see the data is decreasing and then it starts increasing. You could do periodogram analysis to see if there are little fluctuations in that data, high frequency type of modulation in there, but we don't have enough data. But if we have, let's say, a time span of years, or 1 year, we have several data in that year, so we might be able, assuming the star or this process is periodic and I mean, is periodic and is not shifting, because sometimes the star loses angular momentum itself over several years, and then the period of the star changes. So, but you assume it's not changing, then you could fold this data over a long period of time and see if you have something that you can talk about it.
Yep. So the next step, deliverable, is to get all the data, so that we will have everything, all 92 files. We look at the data. If it is usable, I mean, the data is correct, but if we can draw conclusion, that's what I mean usable.
That would be great. That would be great. That would be a nice way to closing this summer effort. I think it was a great start. It's exciting.
So it will be when we meet on Sunday. It will be available.
Okay, so let's talk sometime on Saturday to determine at what time is a good time for everybody. Okay.
But the most important thing for the meeting for today was, does what we have put together make sense? It makes so, because it was.
It does. Yeah.
I mean, using the IDL part.
Yes.
How to use your routines, and after that putting that in Python. So we were thinking, okay, let's do one part to see if it is right. If it is right, we put the rest.
Okay. And Shaunak, if you bump into something, don't waste so much time. Email me, and I can go through that with you.
Okay.
All right.
Just a quick question. I'm trying to get the IDL. I looked at the files that were in the Dropbox. There's no install file for IDL that's 6.
You know what? Can somebody export that to Evccsi? Because it's in my Microsoft.
If not, I can see if I have the IDL installer in my downloads anywhere. I can try looking, and then if I find it, I'll send it to you.
If not, let me know, because tomorrow I'm going to the observatory. The computer, my Microsoft is there, is in the observatory, and I have the IDL routine there. I put it in Dropbox, but somehow it got deleted. I can't find there.
Yeah, so if not, what I can do is I can probably get. Either way, I'm probably going to have to set up a VM in EC2 to run AstroPi. So I think I can get what they call GDL, which is the open source version of IDL.
Oh, really? Oh, yeah. But then you might run into some.
It might not run everything that you guys are running because it's open source and it's a little bit over.
Yeah, well, yeah. Don't. Yeah, I think it's you're gonna have an IDL routine by tomorrow, or
all right,
not cool. Later than Saturday.
All right, cool.
It's a pirate one, but it works. I don't know if it's pirate. Somebody gave me and say, "Oh, it is legal." I work in IDL and I have it, so this is for your students. Okay, great.
Okay, that works.
That works, yeah. All right.
Just a second. Phil is looking at. Oh yeah, this is the.
Yeah, I think I found the installer here.
Oh, you did? Where is it?
No, it's in my downloads.
Okay.
Yeah. Okay. So I have a zip file, and I can actually I can send that to you guys through Zoom right now.
So you need that, and you need a file called license.dat.
Just a sec. I might have it.
You need the installer, and you need
Yeah. I have it. Everything is here. Yeah.
And TXT or DAT, one of those.
Okay,
I guess. Yeah, I guess if you could put that in like the Dropbox or something, that same Drop or whichever.
Yeah, put in the Dropbox. I think everyone has access to the Dropbox, right?
Yeah, I have access to the Dropbox, the EVS one.
And Evccsi, do you have access to?
Yeah, I have access. I got all the files.
Okay.
Files and a bunch of other files from there.
Okay.
Okay, just a second. I can actually send the zip file here in chat if you guys would prefer.
Try now, it's fast.
Yeah.
If it works.
If it works, yeah.
Yeah. If not, I have access to the Evccsi.
Oh, it actually started. Uploading.
Yeah. Yeah, upload speed is
Let me
slow.
go to the Dropbox here.
Yeah, Dropbox is usually fairly optimized.
Okay, let's try Dropbox.
Put it on Salesforce Dropbox.
Evccsi.
Give me a minute. Let me log into the Dropbox here real quick. Let me make sure I can see it. 1 sec.
Yeah, I think just the executable file in the IDL 6.3 directory is not there.
I know, somehow it got deleted. I don't understand.
You can just put it there.
Yeah.
Phil is putting the installation file. Yeah. Okay, it's uploading. Okay, oh, it is pretty fast. Yeah, so Dropbox is much faster. It's much better.
Than Zoom.
Zoom, in the Zoom you can send some kind of Excel file, but not big files. It's uploading.
Yeah, so within the next 5 minutes, it will probably show up.
Okay.
These are the Microsoft minutes. It says 2 minutes left.
And you have the license DAT too, right?
Yeah, it's all in the IDL 6.3 folder.
For some reason, example.
Oh, hold on. Upload error.
Oh, something quite
server error.
Yeah.
We can try again.
Yeah, try again. It doesn't complain that there is not enough space. It says just who knows. Try again. You can share the screen so that they see that too. You can move so that people see.
Yeah.
Okay, upload it 0 wet. Upload error.
More error?
Yeah.
Is it possible it doesn't allow us Dropbox to upload exec files?
Can you just can you email the executable?
Yeah.
Yeah. Okay. We'll do that.
Email the executable and the license.
Yeah.
Those are the two he will need, and then the next thing he needs is to download the library. Process and Astron.
Okay, in the meanwhile, I just created a folder in that same Dropbox. It's called Papers and Notes. So I'll go ahead and put the papers and the papers on.
Rejected because it is big. Can you put it in and share it from Google
so
Drive?
is in Evccsi.
It was rejected. Google rejected it because the file is too big. That's attachment.
Oh, really?
Yeah.
Huh.
What are you trying to again?
I am trying to. This window is.
You're zipping it now.
I'm unzipping it right now.
Oh, okay. I see. You tried from the zip archive. Copied from the zip archive, right?
Yeah.
Okay. That may be a reason. Now try to attach it.
Okay. Now I think we might be able to. Yeah. Okay. I see. Yeah. Now it's uploading, and I will send it via email.
So where are you putting in the 7 members? In the Evccsi CSI?
I'm just emailing the file to you guys because Dropbox
That we do. Okay, all right. Yeah. Okay, and also email the license.
In the Dropbox folder, I think all of the contents are there except for the exe file.
Okay.
So the license is available.
Okay.
License.dat, license.text.
So because you need the license data. When you do the installation, it's gonna ask you to copy and paste that part.
I have the license.dat. I have the license.dat.
Oh, you do have. Okay. All right.
Okay.
It's already existing. So I think it's just the installer.
Right. That's what I'm sending right now.
Okay.
And is this a Windows or Mac installer? I'm just curious.
It's a Windows.
The Windows installer. Okay.
It's a Windows installer, yeah.
Okay, cool.
Half of it is self-loaded for now.
Say again?
It's big. That's why it's 118 megabytes. Okay.
Oh. Oh, were you able to email 118 megabytes?
Yeah, so it's actually being uploaded to Google Drive, and then that link is being shared with you guys.
Okay. All right, that would do it. Well, I wonder if that's what I did.
I wouldn't be surprised if someone, when he was copying the file, he just moved it.
My drive.
Almost there. 100%. Few Microsoft seconds.
All right. Is you trying to go there? Is you trying to upload?
Still uploading, yeah.
Okay.
Okay, so I just uploaded the.
We do eventually, maybe in the next few minutes, if you guys, I mean, if you're already tired, so no problem at all. We'll submit it whenever it's supposed.
Okay. If not, tomorrow I can recuperate this file in my computer up in the observatory.
Okay.
All right. All right, folks. Good job.
All right.
See you on Sunday, and we try to communicate on Saturday. Shaunak, if you need any help, just give me a call.
Okay. Actually, is it okay if I just show you the directory that I have right now? I copy pasted a couple of folders.
Yes.
In there. Okay, so I am add folders and
okay.
Okay, so I have the pro folder has these ones in there so far.
Okay.
I have the veiling and then the TW high. I think these are the records, right? And then the Dropbox folder. I think a lot of this might not be necessary.
No, not necessary. Yeah, that's for the low resolution.
Right. But like the main sequence templates.
Oh, the main sequence. You could put that one together with TW.
Okay.
Yeah.
Okay, so I should move that up.
Yeah, if you could move that, it would be great.
Okay.
Yeah, and place it in there because the main sequence has, I think has, can you open? You should have two main sequence there and the sun. Yeah, it's kind of empty now. You need to have the sun in there, and you need to have J, G, and a few numbers. You have to have the main sequence in there.
We could look at. It should be in the Evccsi folder, or unless it was.
It should be in the Dropbox. Let me see.
The HAVE folder, right?
The templates start with J, GJ something, dash something.
So, okay, so these were.
Let me see if I can. Let me see here if I can put that in a Dropbox.
Oh, yeah, okay, yeah. The file finally finished uploading.
Okay, very good.
Yeah, so I'll send that now.
So this is Celso, Eduardo.
This is everyone in the thread.
Yeah, okay.
Yeah. Okay. Okay. Now you guys should have access to the Evccsi file.
Okay, very good. Very good. Okay, so this is share. Copy TW Hydra. Okay, TW Hydra, you have the data, right? You need the main sequence. Okay, wait a second. Pick the nodes really. Really. Pick the nodes. 6.3. Hydra, new sequence templates, copy, and then here, paste, 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 paste. Upload folder. And then go here. Search my program Hydra. Upload. And so templates. Upload folder. And sequence templates. all files from documents. Only do this if you trust the site. Cancel. What is this? Shauna, can you see the main sequence templates in the folder now? Evccsi.
Sequence.
In Dropbox.
No, I see a bunch of loud something.
Alert from Dropbox.
ADP dot something something that ends with loud.
And in the folder Evccsi.
Okay, they're .iCloud files.
.icon?
.iCloud.
Oh, .iCloud. Really? Which means they are not there?
Not the FITS files, at least.
How do I do this? Because all of this is in the iCloud.
Okay.
Oh boy.
Actually, I'll try downloading one and see if I can do something with it.
Users. Batalha.
Yeah, I think that works.
Okay, let me try again. Let me try again. Home, files, Evccsi, upload file, no, go back, cancel, upload folder, and then go here, and go there. Here and put that behind here and then go to this one, upload. Okay. It's uploading. And Vika's put a paper and papers and notes.
Yeah, so I'll be adding the notes. Notes to come.
Okay.
So I've got about four papers I'm kind of scanning through right now just to kind of start getting a handle on the subject.
Okay. 4 minutes to go. So, Shaunak, you should see that some of the files now are appearing in the folder. They are not iCloud.
Okay.
You have a sunspec.save there.
Okay, yeah, I see. Yes, there's a save file. There's a TGZ file.
Yeah, now there is a TGZ that is coming. I don't know what that is. Oh, that is the fits file.
Mm-hmm. Yeah.
Of the template fits file, kind of collapsed.
Hey guys, I'm just gonna log off since I have a bit of homework to finish.
Okay.
All right. Bye, guys.
We are good.
Bye-bye.
I think we are done here. I'll just let the computer finish uploading.
Okay.
All right.
So, yeah, Sunday we'll have the records ready.
Yeah, everything ready and processed.
Mm-hmm.
All right.
Okay. Bye, guys.
Okay. Bye-bye.
Good night, you all. Bye.